Hello, everyone. Thank you for joining us. We're very excited to talk about the potential of ePTFE. I'm Beth Harrison-Meyer. I am the SVP Marketing of Aptyx, and I am joined by Eric Leopold and Chris Stedham.
Good morning.
Good morning. Whoa.
Our experts.
Everybody's awake now.
They're our experts in ePTFE, and before they give a little more on their background, we'll share some history of ePTFE. But before we do that, we would like to thank Tom Salemi and the Device Talks team for not just this amazing conference, but everything Device Talks does. I'm not sure how many of you saw Von Toronos yesterday here on this stage, which is actually a little nerve-wracking because he was pretty badass. So
Yeah.
Following that up is something. But he spoke about how important these conversations are, and that's why he was here. And, you know, all of us have a shared purpose in medtech and advancing patient lives, impacting them positively, supporting care teams. And this morning at the Women in MedTech breakfast, we spoke about the power of language, and it does have great power, as does knowledge. And sharing knowledge really amplifies it and gives us an opportunity to truly positively impact patient lives. And ePTFE is something that can do that. So we're honored to be here. So again, thank you. So the history of ePTFE is pretty fascinating, actually, and I'm going to bet that quite a few of you in this room don't know much about it. It might even be your next dinner party story. Let's see.
So we'll start first by talking about PTFE before the E came into play. PTFE started back in the 1930s at DuPont. Roy Plunkett was doing a lot of work trying to identify new fluorocarbons. And in doing that work, he came across a slippery white powder in his vat one day when things went a little awry. That material stayed on the back burner. It got some research, and it didn't really come into real use until World War II. So during the Manhattan Project, the material was used for its corrosion resistance properties. It was used for uranium enrichment as a coating surface on one of their containers. So once the war ended and the secrecy order on the material was lifted, it was then picked up by DuPont again, where they were able to patent the material, and the PTFE then was trademarked as Teflon, as many of us know it today. Following that, about 25 years later, Bob Gore from W.L. Gore wanted to create a new material from it. He wanted to add some porosity to it. So he tried different techniques to stretch the material until he came up with the process of high temperature and a quick stretching process that then brought about ePTFE. Gore then traded that as Gore-Tex, which we all know from jackets and different material as used in a lot of the things we use today. Following that, a lot of research continued to happen both with Teflon and with ePTFE, and it was started in the 1970s then where it started hitting the medical device arena. So PTFE, what makes it unique is it has the fluorine element on the backbone of the carbon. That fluorine is a large element. The bond to the carbon is long. It creates a unique properties because of that structure. It creates an organic polymer that has the lowest surface energy. It has the most chemical resistance of all the different organic polymers. It's most thermally stable, and then also it has a high melting point, making it just a very useful material.
Yeah, and then once you expand it, that's where you get the porosity. And the porosity is really what gives it a lot of the benefits we use with medical devices. It makes it a little bit stronger, gives it a little bit more flexibility, makes it permeable. We can control the permeability, so if you want it to be permeable, it can be. If you want cell growth into it, it can be. So it's that stretching that really led to the next generation of implants.
So ePTFE is an amazing material, and we invite you to watch the screen to see some of the many benefits. So, Eric and Chris, this really begs the question. If eTPFE is such a game-changing material, why aren't more people using it to change the game?
It's a great question. And one of the main reasons is there's been a lot of patent protection. There are two main companies that worked with it in the early days. They are Bard and W.L. Gore. And as they used the material, they did strong patent protection that really limited the availability of the material to use in other medical products.
Yeah, I mean, the first litigation that was awarded to Bard was significant, hundreds of millions of dollars. It was contested, went on, it was appealed, confirmed it appealed, willful infringement, up to $800 million plus 20% royalties going forward. That type of protection limits what happens around the rest of the industry. So other companies weren't investigating. And that litigation went on for years and years. And many of the older engineers that had been instrumental in creating these implants had retired. And so that knowledge of how to work with the material, how to use it effectively, was very, very localized in Arizona. And unfortunately just didn't spread around the industry that can really use it. And we hope to help that.
And so the patent ended in 2019 and then something else happened?
Yeah, COVID happened. So, right after that patent expired in late October, there was a little bit of traction and COVID happened. So any of the elective procedures in the hospitals, if you remember, they were restricted quite a bit. And that went on for a while. And then the nature of implant PMA approval in the United States anyway takes quite a bit of time. And so you're starting to see a lot of those products hit the market now.
So we talk about specialized expertise and a couple of companies you mentioned, and I believe the two of you have that.
Exactly. So I started my career working with these different fabrics, ePTFE, polyester, and others. Started that career 30 years ago with Gore. Was able to help develop the Gore Viabond product, iliofemoral device, the thoracic TAG product, as well as the excluder AAA device. And so working with those is the end to get that expertise, get that knowledge base built. Beyond that, I've been able to work with Lombard on the Altura AAA device, as well as the Artivian AMDS device more recently. And we have a lot of other different devices we work on that we unfortunately can't tell you about. But Chris?
Yeah, and I've been working with ePTFE for about 20 years. I started at Cordis, investigating it there. I was in a material science program at the University of Florida, and that's where I was first exposed to ePTFE. Went on to B. Brown, and from there I went to Guidant, worked on an ePTFE balloon with Gore in Guidant. Went on to help start a company called Machine Solutions, and then I went to Bard Peripheral Vascular, where later I was a technical manager for covered stents in Europe. And for the last 9 years, I was with Medical Murray, leading one of our offices and developing ePTFE products specifically in that office.
So a pretty amazing background. So what we're going to cover, a brief intro to Aptyx, looking at materials, key clinical uses and some mitigation there, addressing performance risk. The real heart of what we'll talk about will be key considerations when working with ePTFE, so really how you can get the best out of it and realize its true potential, a look into the future, and then, of course, Q&A. So Aptyx is a global design and manufacturing services provider with over 10 locations worldwide. But what makes Aptyx Aptyx is our team, our make it happen mindset. We like to say that engineering is the heartbeat of the company. And our team loves nothing more than partnering with customers to solve complex challenges. And we do that from D&D to finished device to assembly in specializations such as molding, including injection, dip, and blow molding, extrusion, coating solutions, supporting areas such as automation and tooling, across a range of markets, including interventional that we're talking about today, robotic surgery, many other demanding markets. And while we may be a newish name, our depth of experience is not new. We bring together the aptitude and excellence of more than a dozen companies with a 70-year track record, helping customers manufacture their competitive edge. And we've recently grown our family tree. Earlier this year, we acquired the Charlotte facility of Medical Murray, and that is where both Eric and Chris hail from. And with that, it really amplifies our expertise in the interventional space, specifically transcatheter implants, so ePTFE, but many other materials, also complex catheters, and then the delivery systems to implant or to deliver the implants. So now we'll turn it back to talking about ePTFE and implants.
So when we then look at what are the options we have, ePTFE is a very strong, important material for tissue replacement, for vascular replacement. But there's also tissue. Tissue has the longest history. Using human, bovine, porcine, it just has a lot of history and performance. Polyester also has a long history. Polyester is a very strong material that has performed well for vascular grafts in certain applications. ePTFE, though, as we'll see, has a little more versatility. It has even greater opportunity. So when we look at polyester and its properties, again, they're strong. It's a durable material. It has a good high-level flexibility, strong tensile strength. It's very biocompatible and performs well in the body. And it's also a fairly low cost, which makes it a nice performing material for grafts and some other applications.
Yeah, and looking at ePTFE, it's very modifiable. We can create extremely low profiles. We can create strength in different directions, and we can control how much endothelialization we have with those implants.
So it brings all the benefits of polyester with a little more above and beyond. So as we look at the next slide, it's been used for over 50 years in a wide range and growing range of applications. It started off as primarily grafts that started back in the 70s, and since then, those grafts have gotten more developed, more complex. Sutures came into play a number of years later. Again, strong, very high-performing material for the clinical application. But then as we get a little later, we see an even higher evolvement of the designs and the use of ePTFE, where it starts being used in stent graft systems, it starts to be used on anastomosis and different ways to control the blood flow through the body. It's starting also to bring in a lot of other components into that. And then as we see on the far slide that it's starting to be used for even higher value products like heart valves. So continued elevation of the design and requires even more insights into the material. So when we then look at the clinical risks, every product that's made, all materials used have clinical risks associated with them, and ePTFE is no different. As we look at a simple vascular graft, as it's attached to the native artery, the anastomosis is performed, there's risks that come with that. There's risks of the suture tearing through the material. There's risks of blood weeping through. So as shown in this image, at the end of a graft, you can often get an occlusion, and those are risks that need to be mitigated. And knowing how to design the material, knowing how to engage it with other components within it becomes very important.
Sure, and many companies are doing it. You see them on the market now with other bioactive agents, and you're starting to see some composites come through.
So as we look at the devices as they're created, going beyond the material, there's also performance risks that the overall device can have. You can have mechanical failures. There's interactions with struts and stent frames. There's delamination that can occur as we laminate onto those frames. The ability of the blood to have the properties that you want so that it stays within the artery, and suture retention. Those are just a few of the risks that we have to mitigate.
And all of those properties that contribute to those risks are modifiable. So with proper knowledge and with a little bit of creativity, you can control the porosity to affect how it weeps. You can add composite systems to help with delamination if you're in a tough situation where that's one of the issues that you're worried about. Suture retention can also be addressed with how you orient layers or add composite structures there. So many of the performance risks are easily addressable with the proper execution.
So more expertise, less risk, greater performance. And with ePTFE, there are multiple considerations with how you can work with it. And we're showing 6 different areas here. So is there a sweet spot as far as how you approach it or how you mix and match or?
Yeah, I mean, that's a great question because there are many different variations and types of ePTFE. And when I say types, if we think of ePTFE, it can come in a membrane form, it can come in tubular form. We can create flat sheets and it comes in a fiber. And depending on the clinical application, we may want to use a membrane for a very complex shape where we need ultra-thin properties and we want to build out different elements. If we need high flexibility, like a graft, tube form is fine. If we're looking at structural heart applications, a lot of it is a combination and usually uses flat sheet technology. And of course, fiber in sutures, a lot of times ePTFE is sewn onto frames using ePTFE suture as well.
So when we look at how do you make ePTFE, this is looking at just one process which is used to make the thin film, the thin membranes that we often use on stent graft systems. So it starts with that white slippery powder. That material, the way you control it, the way you store it, what you bring into play at the beginning with the solvents and lubricants, all those things help control what output you're going to get. It then goes through a mixing, aging, and preforming process leading up to the paste extrusion. And again, as you're doing that ram extrusion, you can change your pressures, you can change the temperatures, you can get different fibrils within that material. There's a lot of process controls that happen throughout this process.
Yeah, exactly. And so coming out of the ram extrusion, you still have basically PTFE. And that first stretching happens during a calendaring process where it goes through a rolling system. There can be multiple rollers. They can be heated. And how it's pulled through those rollers, how much pressure is put into those rollers, the initial thickness going in, all controls a lot of the porosity and a lot of the parameters coming out of the rollers. And that gives you your initial machine direction orientation and porosity systems. And then from there, if we want more, we can put it into a tenor frame on the membrane side and create our transverse orientation and create biaxial properties.
So we don't make the ePTFE ourselves, but as I understand it, we often give input into the actual process.
Yeah. Yes, we partner with several different companies to get the output we're looking for because the requirements you have for a device vary from device to device, and it's important that you control it from the beginning.
Yeah, so we work with our partners. We specify the resins directly into their selection. We work with them on the extrusions itself, looking at different drawdown ratios, how much shear gets put into the material, and as well as expansion ratios all the way through the processing. And that allows us to have different properties for our finished devices however we want to attach it to the end product. So here's a perfect example. So many people may not be familiar with the differences between uniaxial or MDO ePTFE. That's more what you would see in a vascular graft. And on a membrane side where we put it through a tenor frame and we get the transverse expansion, that's what you see on the right-hand side. Both equally biocompatible, just have very different properties. The one on the right, much thinner, potentially much denser if how we want to build it out. but we can also increase the porosity on the biaxial side. You can see how on the uniaxial side, you can see how that material may have been stretched in one direction and still has some room to be stretched in the other. We can control those ratios and fully expand material, partially expand material, depending on the properties we want with the finished device.
When we look at another alternative we have, and that's building a structure, it's layering the material, it's adding other materials in. A very common one is adding heparin to vascular grafts in order to improve the thrombogenicity reactivity of the material. So adding these different bioactive components, adding layers, allows us to really dial in the material for the given application.
That's where your inner Gore is showing with the heparin.
So Gore likes heparin, but Bard likes the carbon. So there's different applications that can be provided. A lot of them can give you the same final targets, but dialing those in is really critical to getting the right performance.
Yep. And I think the key takeaway is it's very versatile. There's many different materials. There's many different additives. There's different combinations of how to use the material that all creates a wide variety of finished devices. Here's a perfect example. Many people may not be familiar with this particular device. This is a physician-manufactured device in Japan. Culturally, they don't use porcine heart valves over there. And so Dr. Yamagishi developed a valve using ePTFE. Those sinuses are expanded and the leaflets are sewn. And so this is a fully ePTFE valve that's had years of experience in the Japanese market.
The other direction we can go is we can add a framework inside of the ePTFE. We can do a laminating process. This is where you are able to drive a lot of the performance out of a device by adding in the nitinol frame, by attaching the ePTFE to it, by adding radiopaque markers. You make really a device that goes above and beyond the original graft materials.
Right, and anytime you're pushing technology, there's some watch outs. With ePTFE, especially if we're encapsulating and sintering, we have to watch out for the high temperature processing that we're doing and the impact it may have on the substrates that we're working with. Delamination of any time you're putting two materials together, you want to make sure they stay together. So that sintering process or sewing process, or however we're going to use a composite structure to improve the adhesion, are all important considerations. Also, anytime you're loading any implant, you want to make sure that you're not tearing materials. And a previous consideration we talked about was suture pullout strength, suture retention. And so making sure that we adequately address those as well.
Now, I've heard you talk about an example with ePTFE, you don't need to sew versus, say, if you did it with polyester, so it's going to be much quicker, less cost.
That's exactly right. When we can encapsulate and bring those materials together satisfactorily, that can be an extremely fast process, where if you've got a graft system like this can be many hours, potentially over a day of sewing and processing, and we can do the encapsulation through the sintering process in under an hour.
So where do we go from here? Where does the ePTFE have future development? And it goes in a lot of different directions. On the screen are a few of the considerations that are being worked on today, and some of them that we're working on. Material combinations, for instance, is, again, more bioactives are being developed, are being engaged with the material, the ways that we can control the properties and the engagement with the artery is really important, as well as adding new physical properties to the material by adding new layers and creating new compounds, essentially.
Yeah, I mean, those new compounds are real, and your imagination is the only limitation we have. We can do some really interesting things. Also, moving the profiles down. ePTFE, we can work with ePTFE that's 1/10,000th of an inch human hair's 3,000ths. So you can do the math. It's a complete factor, more than a factor, lower in profile. Sensor integration, and because of the porosity that ePTFE has, you can use it for drug elution as well. So there's many capabilities that you'll see coming to market over the coming years.
So it really is a game-changing material. And if you don't feel that way right now, please don't blame the ePTFE, blame us.
That's fair. Yeah, and we all want to make the best device possible. All of us in this room want to impact lives, improve healthcare, and improve the outcome of patients. That's why we got into the industry. I really believe ePTFE is a material that can help do that.
When lives are on the line and every choice matters,
Please consider the power of ePTFE.
I wanted to ask you both about the most impactful product that you've worked on in the past, because I know we can't talk about things in development.
So for myself, working at Gore, the AAA device I worked on there, it's life-changing. It has properties that were unseen at the time, and really brought a new technology to life. It was a game-changing product. So something to be proud of, and definitely enjoyed that.
Yeah, that's not fair. Eric wins. I can tell you now, that was a pretty amazing product. My experiences with vascular access grafts with Bard and the covered stents that came from them that are commercialized. We have some really exciting ePTFE products that are coming to market soon that I'll love to be able to share with you once they're public. But yeah, Eric definitely wins on the commercialized product, hands down.
You want to tell the story?
So non-commercialized, the reason I'm really passionate about ePTFE is my father suffered from vascular disease and had to have artificial arteries implanted many, many years ago. Unfortunately, before Eric's product was available, he would have been much happier. But those vessels were very stiff, and the attachment technology at the time, he just never really recovered from. And since that point, although he was also very upset with his Foley catheter, he really wanted me to improve some of this work, some of this technology that he had been put into him. He knew I was in this space, and so it's always been very important to me to make improvements where I can. And ePTFE has allowed me to do it.
That's an amazing story. It is why we're all here.
Yep.
Well, thank you all for attending.
you.
We do have information on ePTFE if you are interested in getting it, and I think some great Aptyx pens as well. They're the best pens, I promise.
They're actually pretty good.
Well, if anybody has any questions, feel free to check with us after. Thank you.
Thanks.